Hello. In this video lecture, I will introduce and describe boosting, which is the last tree-based method that we will discuss. So, boosting, like bagging and random forest, is a general approach that can be applied to many statistical learning methods, either regression or classification. Here we will focus to regression and to decision trees, but the idea can be applied to not just trees, other statistical learning methods. Okay. So just recall that bagging involved creating multiple copies of the original data, so bootstrap data sets, right? And then we fit a separate decision tree to each of the bootstrap data set, and then we combined all these trees so that we get a single predictive model. Okay, so that was bagging. So what was particular about it was that each tree was fit on a bootstrap data set that was independently sampled with replacement from the original data set. So there was the hope was that each of the trees are roughly speaking independent. Okay. Now boosting is similar to bagging in that it combines many trees. Okay. But the difference is that bagging, the difference with bagging or random forest is that bagging in random forest, we're fitting trees to independently sampled bootstrap data set. So in a way, it was doing parallel fitting, whereas boosting the trees are grown sequentially. So each tree is grown using information from previously grown trees. Okay, and boosting does not involve bootstrap sampling. So what happens is that in boosting, each tree is fit on a modified version of the original tree. In contrast to bagging and random forest, each tree is not grown deeply. So each tree is a very simple tree, has only a few D-terminal nodes. If we have a large tree, we have overfitting. If we have a small tree, it will be a weak learner, will have a low flexibility. But the idea is that since we grow these trees sequentially, each tree is taking care of whatever pattern in the data that the previous trees were unable to capture. So how does that work? So at any stage we have a model, we fit a decision tree to the residuals of the model. And here's the algorithm. Just take a look a little bit. So unlike fitting a single large decision tree to the data, which can lead to overfitting. The boosting approach learns slowly, and this is the slow learning part is here. Okay, so at any iteration we have B iteration, and at any iteration we have a residual. At the beginning we start with the function f hat, which is 0, and the residual, obviously, if the function is predicting 0 and the response is y, what is the residual? yi minus 0. So the residual is yi for all the data points in the training set. And what do? We fit a tree f hat b, let's say the first tree, with d splits, meaning d plus 1 their terminal nodes. So if d is 1, that means we have 2 nodes to the training data. So our response is not y anymore, it's the residuals that we have. So each tree is trying to capture what's left in the residual, to take that out. In the second step, we add this new decision tree f hat b. B is the beat iteration. It goes from 1 to b. This b is different from the bootstrapped trees. B is just capital B here is uppercase B is just the number of iterations. So how do we add this? We have a current sum of trees f hat x, and then we have a lambda here. This lambda is different from the tuning parameter we saw in regularized regression. This is what we call a learning rate. Okay, and it's typically a small number, 0.01 or 0.001 or 0.0001. So the smaller the lambda, the slower the learning. Again, I want to emphasize the splits in boostings are small, and because the trees, each tree is very small, it can slowly improve f hat, okay, in areas where it does not perform well. And how do we know the areas it does not perform well? By fitting the tree to the residual. And then this is the updated tree. Then we take that, whatever it is, whatever prediction it makes, and we remove it from the residual. So we have a new residual. So here we can say, okay, let's fit a new tree to this updated residual, and let's find a tree that can improve f hat in areas where it does not perform well. Okay. So one important point is that each tree, the construction of each tree depends strongly on the trees that have already grown, because the construction of f hat b little b depends on the residual at this moment, and the residual at this moment depends on the trees that have already been grown. Okay. And we do this b times. And you see here there are a couple of free parameters. One is the number of trees. One is lambda, which is the learning rate, or it's also known as a shrinkage parameter. But I call it the learning rate. And then the number of splits. Okay. So a large B, unlike boosting and random forest, where B B anything beyond 500 would be okay. Large B can lead to overfitting, but very slowly. Okay. And the book suggests that we use cross-validation to select B, but I want to add something here, that tuning B is not as crucial as, for example, tuning lambda in ridge and lasso. Okay. And a few thousand is probably okay. So we don't want to kill ourselves to cross-validate B. That's what I want to just emphasize. Lambda, also known as the learning rate, as I said, the smaller the lambda and the larger the needed B. If lambda is small, the learning is slow, but methods that learn slow tend to perform better. And the number of splits in each tree. And the number of splits controls the complexity of the boosted ensemble. Again, each of these trees has D+1 terminal nodes. We want to have many boosted trees that are weak learners, but together they do a great job. Here you can see, take a look at the classification example. Here we have the test classification error, or focus is not classification, is regression, but the take-home message we want to get from this slide is independent of the fact that this is a classification problem. The take-home message are as such that first of all, boosting has a better performance than random forest, as we can see. Boosting with depth 1, which means a single split, or depth 2, which means 3 splits, is not very different. Actually, one split is better. I don't know if you can make a general statement about that because these two are close, and I think depending on this data set, one or two, one of them might be better than the other one. And I wouldn't, again, spend a lot of time playing with the, I mean, yes, if play with parameters and experiment with them and see what the results are, but in a real life situation in the industry, I wouldn't, unless I have a good reason, I would just go with a depth 1, 2, or at most 3. The number of trees, as we can see, after a few thousand, does not have a significant effect on the classification error, and that's why I also mentioned I wouldn't spend a lot of time on cross-validating the number of trees. I would just try a few, like 1,000, 2,000, 3,000, 4,000, and then see if you get something like this, and then if this is it, then that means that a few thousand is sufficient. Okay. Finally, a tree that has a depth of 1 means that it has 2 terminal nodes, so it's just a single split. And a single split is a tree with a single split is also known as a stump. And if you use trees that are made out of stumps, then the boosting for regression trees can be reduced to an additive model, which is easier to interpret. Okay, next we will show a simple example on R, how to apply boosting to predict the median house prices in the suburbs of Boston, and how to evaluate the importance of variables. So we use the GBM package, and within it the GBM function to fit boosted regression trees to the Boston dataset. We use the option Gaussian because this is a regression problem. If it was a binary classification problem, we would use the distribution as Bernoulli. Okay, so let's just look at GBM. Here we have the formula, the distribution. Here it says Bernoulli. So Gaussian, it will be a squared error. If we wanted to fit a boosted trees where the error is the absolute loss, meaning the instead of the squared loss, it's the absolute value of the residual, then we would use Laplace. If we are doing a classification, we Bernoulli. And there are many other options, which we won't discuss, but this is just a good practice to look inside what are the options, the defaults, the interaction depth. The interaction depth is, what is the interaction depth? The interaction depth is, or D. The number of trees default is 100. Shrinkage, which is our learning rate, is 0.1. And weights is if different data points have different weights. I think that's it. It's pretty straightforward. Okay, here we say the interaction tree, let's say it's 1, and we have the number of rows, number of observations, number of training, and then we have the boosted tree. And let's just run this. Let's forget about that. Then we have summary. Oh, it's not summary Boston. I wanted summary of boosted Boston. And we see that RM and LStat are the most important ones. Okay, so let's do this. D1, it's D1. Okay. And then we can do D2. I just want to show you the effect of the number of trees. So you see the order of LStat and RM can change, but both of them are the most important ones. Okay. Now let's look at the let's change the learning rate. Well, let's first do some predictions. Y hat boost D1 is predict the boosted object. New data is Boston, everything except the train, all the roads. What is the mean squared error? Oh, let's make this test. Okay, let's take some of the stuff we had before. Oh, it's 20. Okay. Now I want to play with the learning rate. I want to see what the function was again, GBM. Okay, what is verbose? Okay. So we want shrinkage. The default is 0.1. So let's see what happens if we shrink it to make it smaller. Okay, you see a small change. Let's make it much smaller. Okay, now because the learning rate has become so small, maybe we need more trees. It would take longer. You see, more trees led to some improvement. And let's just make this bigger, and then we see increase. Okay, so we have you see there the number of trees and the shrinkage, they play a role, but it's not as big of a role. Now my guess is if I decrease the number of trees, it will improve the performance. Well, slightly. Let's see if we make it much smaller. Okay. All right. Well, that's that. Okay, so let's remove this part and let's add these two, just so we know what's the effect of the size of each tree. Again, these two are the most important ones. Okay, this is the error. 19. So I'm curious what happens if we go to 4. These two are still the most important ones. Okay, we get some improvement. I feel there is something. Let's change this. Let's play a little bit. The shrinkage. Let's run this from the beginning. Let's take this up there. Okay. Let's organize our code a little bit so we can read it better. Let's take it away. Okay, let's just check everything. Here's the number of rows. Here's the training set. Let's make this bigger. Just curious to see if we can get a better performance. Slightly, but not much. Alright, so you can play with these parameters as we saw. Again, the number of trees matter. We don't want too many trees because that can lead to overfitting, but we saw that's not a big factor. We want to, the smaller the learning rate or the shrinkage is, the larger the number of trees we need. And we see it's pretty straightforward to use boosting in R and also to create importance plots and evaluate the performance. Okay, so this summarizes chapter 8, tree-based methods. This ends chapter 8. Thank you.